Hello everyone. Let's discuss the questions at the page number 12 about the gaseous reactions. Right? Let's start with the question number 2. So the question number 2 says below reaction occurs at temperature above 100. A plus 3B gas goes to D gas. The reaction is there. The Roman number 1 says when 0.3 moles of A gas and 0.7 moles of B gas kept in a rigid vessel at 27 Celsius, the pressure of the vessel was 1 into 10 power 5 pascals. Right? Let's draw that thing. Right? The first situation, you have a vessel containing A gas and B gas. The amounts are 0.3 and 0.7, right? The amounts are 0.3 and 0.7. And then kept in a rigid vessel at 27 Celsius. So temperature is given as 27 Celsius. Then the pressure of the vessel was 1 into 10 power 5 pascals. Right? 1 into 10 power 5 pascals. That was the pressure of the vessel, right? Calculate the partial pressures of A gas and B gas at 27 Celsius. That was the first question. The partial pressures of A gas and B gas, that is what they are asking. So that is very easy, right? So we have a equation called as the Dalton's partial pressure law. Here the partial pressure is equal to mole fraction of the constituent substance into the P total, right? Total pressure, that is the Dalton's partial pressure law, right? We can apply that thing. Total pressure is given and the mole fractions can be taken as the number of moles of all the substances are given, right? So let's apply that law to the gas A to come up with the partial pressure of A. Right? To gas A, we can write PA is equal to XA, mole fraction of A into P total. Right? Mole fraction of A, that is actually number of moles of A, that is 0.3 divided by the total number of moles. The total number of moles is the addition of these two, that is 1 mole into P total. P total is 1 into 10 power 5 pascals. So the partial pressure is given as 0.3 into 10 power 5 pascals for the gaseous component A. So if you are thinking of the gaseous component B, so partial pressure of B can be taken as the total pressure minus the partial pressure of A. That is Dalton's other law. Right? The summation of partial pressures should be equal to the total pressure. That means PA plus PB should be equal to P total. So if you are subject to PB, that will be P total minus PA. So the P total is given as 1 into 10 power 5 pascals. And PA is actually, we have found that value, 0.3 into 10 power 5 pascals. So the number will be then 0.7 into 10 power 5 pascals. Right? That is for the PB. Right? So these are the answers for the problem number 1. That is very easy, right? Okay. See what they ask in the Roman number 2. When the vessel was heated to 127 Celsius, 0.2 moles of A was reacted with B gas to produce D gas. Right. See what they are saying. What they have done. They have heated this vessel. Right? Vessel was heated. To 127 Celsius. Right? So the system would look like this. We had the vessel now at 127 Celsius. This is the initial situation of actually before the reaction at 127. The system, it is before the reaction at 127. So there the A gas and B gas still appears before the reaction, right? So 0.3 moles of A and 0.7 moles of B would appear before the reaction at 127 Celsius, right? Instant, a millisecond before the reaction at 127. After the system is heated to 127, before millisecond of the reaction, the system would look like this. That is referred to as the initial state. Initial state at 127 Celsius, right? Then what happened? Some reaction occurred, right? Some reaction occurred, right? And that reaction consumed 0.2 moles of A, right? Reaction occurred and that consumed 0.2 moles of A, right? So reaction happened, right? Reaction occurred, and when the reaction happens, that A gas will consume with 3 of B gas. This is the reaction. A gas, here, A gas will consume with 3 of B gas. It's a partial reaction to produce D gas, right? That reaction occurred and 0.2 moles of A was reacted. That is what they are saying, right? This is again the system at 127. The final system, or we can refer to it as the equilibrium system. Right? So at the equilibrium system, the unreacted A, the unreacted B and the so produced D would appear. Unreacted A, unreacted B and so produced D would appear. So a double arrow reaction means none of the reactants would totally consume. None of the reactants would totally consume. That is what a double arrow reaction means. A partial reaction, incomplete reaction. So none of the reactants will totally consume. No limited reagent there. So that unreacted A, the unreacted B, and the so produced D would appear at the end of the reaction. So the end of the reaction of a double arrow reaction is referred to as the equilibrium situation. End of the reaction of a double arrow reaction is referred to as an equilibrium, right? If it was a straight arrow, then we can say it as the real end of the reaction. But for a double arrow reaction, it is referred to as the equilibrium, right? They are the unreacted reactants and the products will be there, right? So let's construct our ICE table for this system. ICE table, right? I means the initial number of moles. C is the consumption or the change. Change occurs when the reaction occurs, right? Change happens, this state happens with the reaction, right? This is the change in the reaction, right? According to stoichiometry, that change always occurs. The reaction always occurs according to stoichiometry. So the change, the number of moles of change always occurs according to stoichiometric ratio, right? And finally, you have the equilibrium situation. The moles of that is will be filled at this row, right? Okay, so always we are drawing these ICE tables, the reaction tables for constant temperature and volume situations, right? So for all of these values, right? Temperature is equal to 127 and volume is a constant. Remember that. Right. Now just try to fill these values. Just try to complete the table here. Right? So they are saying at the reaction 0.2 moles of A was reacted. They are saying at the reaction, right? 0.2 moles of A reacted. Right? Okay, that is also a data given. Alright. Okay, let's insert these values to our ice table. Right? Insert these values to our ice table. Right? So the 0.3 moles of A at the beginning of 127 Celsius at the 127 Celsius before the reaction, before milliseconds of the reaction, 0.3 moles of A was there. So this is this value at the initial 0.3 moles of A and 0.7 moles of B was there. And at the initial point, there was no D appearing before the reaction, right? So at the change state, when the reaction occurs, they are saying 0.2 moles of A reacted, 0.2 moles of A reacted, right? So this is the change. 0.2 moles reacted. That means minus. Reacted, consumed from system, decreased from system. When something is reacting, that means consuming at the reaction, that means that amount will decrease from the system. Right? These are the data they have provided. Right? Okay. Let's try to complete the stuff. Right? So the change state always occurs according to stoichiometry. The change state always occurs according to stoichiometric ratio. The stoichiometric ratio, right? Always occurs according to stoichiometry. Right? Change state always occurs according to stoichiometry. So if 0.2 is to react from A, right? 3 times of that amount should react as B. So 0.2 for one portion, for 3 portions it is 0.6 reacted, consumes, minus values. Right? Consumes. So then 1 mole of A is to react, 1 mole of B will produce. So if 0.2 to react from A, the same mole will produce as B. It is produced, right? Produced, added to the system, produced. The amount will increase with B, right? Okay. Then we'll come up with the final values then. At the end, you have started with 0.3 of A, 0.2 was reacted, so that the end value is 0.1 for A. 0.7 was there at the beginning and 0.6 were reacted, that means 0.1 will be there as moles for B at the end. And initially you had nothing with the D, but the reaction formed 0.2 moles, that means at the final situation you have 0.2 moles of D. Right? With this reaction table, ultimately this gives you N total as the summation of this as 0.4. 0.4 is the total amount of moles at the end. Right? This is your reaction table. So let's use this thing to solve the 2 questions they are asking. Come with the solutions for 2 questions they are asking, right? Okay. So what are the 2 questions they are asking? They are asking you the partial pressures of these guys after the reaction, and then the total pressure of the system at 127 at the end of the reaction. That is, those are 2 things they are asking, right? So partial pressures can be found by applying this equation. For that, you should know the mole fraction as well as the total pressure. So mole fractions can be found with the use of reaction table. So individual number of moles are there as well as the total number of moles is there. so that you can clearly come up with the mole fractions with the use of this reaction table. But the thing is, to come up with the partial pressures of individual components, first you should know the total pressure as well. But here, the total pressure is not given. So we should come up with a method to find out the total pressure of this system. Right? Let's try to come up with a better way to find out the total pressure of this system. Right? So to come up with the total pressure, right? To come up with the total pressure of the system, right? Here we can use the method of proportionalities. Right? So let's discuss how to use proportionalities to find out the total pressure here. Find out the property required. Let's use the method of proportionalities, right? Okay. So here, what we need is to come up with the total pressure first, right? Total pressure is our goal here, right? Total pressure is our goal here. So we are trying to come up with the total pressure of this system, right? This system, P total, that is what we are referring to, right? We need to come up with the total pressure, right? Let's discuss about this method of proportionalities, how to use that thing, right? The thing is this, lamine, right? If you need a number for pressure, you are always expected to relate that system in this case this one, that system with a system you actually know the property. In this case it is a pressure. You have to relate this system with a system actually you know the pressure, actually you know something about pressure. So out of these three systems, right, you know about pressure at here, you know the pressure at this system. So you are expected to relate this system, the system at equilibrium at 127 Celsius, to the system at 27 Celsius initially, before the reaction. So we are expected to relate this system to this one so that we can find out the pressure. The logic here is, if they are asking you a property, you have to always relate the system you require with a system you know, a system you exactly know the required property, right? So if they are asking about pressure, you should relate the system with system you exactly know about pressure, right? If you know about pressure, so you know about pressure with this system, so if you relate these two systems, definitely you can come up with the pressure. Let's see how to use the proportionalities to come up with the pressure at here, right? Okay, so let's come up with the method of proportionalities, right? So I'll write that thing here, right? It's here, right? So I'm relating this one and this one. First the needed one, that is, right, system at 127 equilibrium, right? Consider systems, right? 127 equilibrium, consider systems, (127 Celsius equilibrium and 127 system equilibrium, right? And this one, 27 Celsius, right? 27 Celsius beginning. Consider these two systems, 127 equilibrium and 27 Celsius beginning. Right? Let's consider those two systems. So if you apply the P equals NRT to these two systems, right? For both the systems, right? Volume is a constant. Volume is a constant as we are dealing with a rigid vessel. Rigid vessel means, right? The vessel won't expand or shrink. The volume is going to be a constant even though you have to change the temperature, right? So volume is a constant for both of these two systems, right? As well as R is always a constant. So when considering these two systems, right, as V and R are constants, right? P is proportional to NT. P is proportional to NT. So P is proportional to NT. This will be NT. Proportional, right? So let's apply for these two systems, right? So this is for the 27. So first for the 127 system. 127 Celsius system. So when apply its pressure, that is what we need, P total proportional to N. Now it is total system we are dealing. So P total comes up with P N total, right? That is 0.4. Temperature there is 127. So that is 400 Kelvin. That is number one. So 27 Celsius system, pressure is given as 1 × 5 pascals, proportional to number of moles there. So we are dealing with total things, right? Total pressure is 1.5, 1 × 5 pascals. That means total number of moles with total pressure and total number of moles should be applied. That is 1 mole into the temperature, that is 300 Kelvin. So if you solve, if you divide 1 by 2, you will get P total of 1 × 5 pascals. That will be equal to 0.4 into 400 divided by 1 into 300, right? This gives you your P total as So we can simplify this stuff, right? These two will cancel out, right? So you have here 1.6 over 3 into 10 power 5, right? Right now, P total is going to be 1.6 over 3 into 10 power 5. So the value is 1.6 into divided by 3 means that is 0.5 15, right? So 1 is remaining, it's 3, you know. So this is going to be the total pressure of system at 127 Celsius, right? So see how we have supposed to solve this one using a method of proportionalities, right? Always when considering a proportionalities, right? If you are looking for a pressure, always relate that system with the system you know the pressure. If you need to come up with a number of moles, just relate the system with the system where you exactly know the number of moles. Right? That is the simple idea, right? So here you can use that to count with the total pressure like this. So if we are okay with the total pressure, right, then we can count with the partial pressures as well, right? Let's count with the partial pressures of these three guys there, right? So I'll write the partial pressures right here. Okay, so number 2, the partial pressure of A is equal to XA P total, right? So XA is going to be, right? Sorry, the partial pressure means Roman number 1, no? XA is going to be the number of moles of A divided by the total number of moles. The number of moles of A is 0.1 divided by the total number of moles, that is 0.4 into P total. But now is this. I'll put it as like this, no? 1603, no worries, no? So 1.603 into about 5 squares. So I would find it easy to solve the substitution like that. So this is going to be like 4 is there. 4 is there. So 1.6 over 4 is just 0.4 divided by 3 is going to be 0.133. That's partial pressure of A. So partial pressure of B is also equal to same value because with both same numbers are applied. So partial pressure of D I'll count it, right? I'll count the partial pressure of D and then partial pressure of B is same. So partial pressure of A as well as B is same. So if you are referring to partial pressure of D, you can apply the same equation. PD is equal to, right? PD is equal to mole fraction of D into P total. The mole fraction of D means the number of moles of D, 0.2 divided by total number of moles, that is 0.4 into P total, that is this value, 1.603 into the power 10 power 5. So simplification will give you, I calculate 2 times of this thing, 2 times of this thing, that is 0.266 into the power 5 plus plus. Those are the values for the partial pressures. This is the value for the partial pressure of A as well as B. This is the value for the partial pressure of D. Right? This is the P total value. Right? So this is P total value. So this is the answer for the Roman number 2. Right? So that is how we are supposed to solve this kind of question with use of proportionalities. Right? Okay. Let's complete this stuff. Let's do the question number 3 then. After this, let's move to question number 3. Right. Let's now do the question number 3. See what it says. Consider the following reaction which occurs above 300 Celsius. 300 Celsius. Only above 300 Celsius this reaction occurs. The X plus Y gives you the 4 of Z gas, right? Okay. When 0.2 moles of X gas and 0.3 moles of Y gas were kept in a glass vessel at 25 Celsius, the partial pressures of X gas was 280. Right? See, let's write that system. So we have a system like this. Okay. There are 0.2 moles of X gas and 0.3 moles of Y gas were kept. X gas and Y gas were there. With X gas, it was 0.2 moles. With Y gas, it was 0.3 moles. Right? Okay. At 25 Celsius. At 25 Celsius. Right? Now I change that to 27 Celsius. Right? It should be 27 Celsius. Right? At 27 Celsius. Right. The partial pressure of X gas was 280. The partial pressure of X gas was given, right? So Px also given as 280. Partial pressure of X gas was 280. Then, when the temperature was increased to 327, the above reaction occurred. Then they have increased temperature. Right? Temperature increased. So, at the instance, at the first instance of increasing temperature, the system looks like this. It has increased to 327 Celsius. Right? Before the reaction, after increasing pressure, just before the reaction, the system is only with X gas and Y gas, right? Because just before the reaction you don't have any Z is forming. Only after the reaction occurred, the Z will form, right? So just before the reaction, after increasing temperature, the system would look like this, right? And this is referred to as the initial state. Initial state before the reaction, right? And about reaction occurred. So reaction happens. Right? Reaction occurred. What was the reaction? The reaction is actually X gas reacting with Y gas. Produce that 4 of the gas. Yes, that reaction occurred. And the remaining amount of Y gas was 0.2. So what they are saying is, at the end, the remaining amount of I-gas is given as 0.2 moles. 0.2 moles. Right? So this is the ultimate state, and this is also a double arrow reaction. So again, we are referring to equilibrium state. Right? So as it's a double arrow reaction, none of the reactants will totally consume. So that definitely unreacted X will also appear at the end, as well as the so produced Z will be also there at the end, at the equilibrium. Right? These guys are there. We need to calculate these numbers. So that can be done basically using the reaction table. Right? Okay. So these are the things they have given, the data they have provided. What they are asking is the find out the following after the reaction. After the reaction, what they are asking is partial pressures of Z gas and total pressure. The two things they are asking is partial pressure of Z gas, right? The first thing they are asking is partial pressure of Z gas, PZ. And second thing they are asking is the total pressure of system. These are the two things they are asking, right? So we put as A and B. No? Partial pressure of Z gas and total pressure of the system. Alright, see. So now, first of all, let's construct the reaction table. First of all, let's construct the reaction table. So that will help us to find out the mole fraction we need to find the partial pressure of Z. So partial pressure of Z is the mole fraction of Z into P total. So the mole fraction of Z can be found using the reaction table, as the reaction table provides you the ultimate number of moles of Z as well as in total, right? So we will use the reaction table to calculate the mole fraction of Z, and if you are able to find the P total as well, you can calculate the partial pressure of Z, right? Okay, let's construct a reaction table to calculate the number of moles appearing here at the equilibrium state. That will lead to the mole fraction of Z, right? Okay, so let's calculate the reaction table. So I write the reaction table. So in here the reaction table occurs, right? The change occurs. Right, here the reaction change occurs. Right, right. Construct the reaction table, right? The reaction table is constructed for this, right? This section. Reaction table is always constructed with system where some reaction is happening, right? Okay, not here. After the temperature is increased only, the reaction occurs, right? So reaction table will be constructed for 327 Celsius, where the reaction occurs, right? Okay, so let's calculate the reaction table, right? Reaction table. Okay, reaction table is the ICE table, right? So we have the initial amount of moles, change moles, as well as the equilibrium moles in the reaction table. So what is the reaction there? The reaction is actually X gas reacting with Y gas on ratio, right, to form 4 of Z gas. Notice it's kind of a partial reaction, right? That means none of the reactants will totally consume, right? So that is the reaction. It's a double reaction, right? So that's it. Let's apply these numbers here, right? At the beginning, 0.2 and 0.3 are there. 0.2 is the starting amount of X moles. 0.3 is the starting amount of Y moles. You don't have any Z at the beginning. Right, we construct this table. Keep in mind that we construct this table for 327 Celsius. Right, and volume is should be a constant. Right, so what other data they have provided? They have provided that at the end 0.2 moles of Y is there, no? That was given. So, right, they are saying remaining amount of Y was 0.2. The remaining amount of Y was 0.2, right? That was given. So that value is here. 0.2 is the remaining amount. At the end of the process, the Y amount is 0.2. Right. Let's try to complete this relation table. Right. Let's try to complete this one. So we are always supposed to start completing the relation table from a column, right, where you have only one blank. So with this column you have two blanks, with this column also you have two blanks, but with this column you have only one blank. So this should be the place to start filling the relation table, right? So let's start with this column, right? So you have started with 0.3 moles. At the end only 0.2 moles appear. That means 0.1 moles should consume at the reaction, right? You started with 0.3. At the end only 0.2 appears. That means 0.1 should consume at the reaction. 0.1 should consume. Consume means minus, right? So always a change step happens according to stoichiometry. Always a change step happens according to stoichiometry. 1 to 4 ratio in this case, right? So if 0.1 moles of Y2 react, the amount of X react will be also the same as X to Y are with 1 to 1 ratio. X and Y are with 1 to 1 ratio, right? So Y2 is it 1 to 4 ratio. So if 0.1 mole of Y to react, 0.4 moles of Z should produce. 0.4 moles of Z should produce, as the ratio is 1 to 4. Z will produce. Produce means this will added to the system, right? So at the beginning you haven't had any Z, but now you have, and at the reaction you have produced 0.4 moles of Z. So at the end 0.4 moles of Z should appear. At the beginning there was no Z, but with the reaction 0.4 was produced. So at the end 0.4 should appear. At the end, at the beginning 0.2 moles of X was there. The reaction consumed 0.1 moles. That means at the end 0.1 should appear, right? Beginning 0.2 moles was there with X, 0.1 was consumed, and at the end 0.1 should appear, right? So this gives you your N total as well. So your N total is going to be now what? 0.2, 0.4 and 0.1, that is 0.7 moles. In total is 0.7 moles, right? 0.7 moles. Right, so basically to come up with the partial pressure of the cell, we now know the mole fraction. The partial pressure is given by mole fraction of P total. We know the mole fraction of Z because the number of moles of Z is known, as well as the total number of moles, that is mole fraction of Z is known. Right, but the problem is to come up with the partial pressure, you need to know the P total as well, total pressure also as well. So let's try to come up with this P total first of all. After finding the P total, we can think of finding the partial pressure of Z, right? Okay, so let's try to come up with the total pressure, right? Total pressure in this case, right? So how to come up with the total pressure? How to come up with the total pressure, right? Okay. So first I try to come up with the total pressure, right? So this is our problem now. This is our task to come up with total pressure. Total pressure, that is our goal. So let's use the method of proportionalities. Let's use the method of proportionality, right? So we have to find a pressure data. We are supposed to find a pressure data. So we have to relate that system. You need to find with the system where you know the pressure data. We know about the pressure, right? So as you need to find a pressure data here, right? So you need to relate the system with a system where you actually know the pressure. actually no kind of a pressure. It could be a partial pressure or it could be a total pressure, no worries, right? You have to relate this system to a system where you exactly know the pressure, right? So what was that system? Not here, but here some pressure data is appearing. Some pressure data is appearing, but not with the total amount, but with some partial, with some gaseous component. It's a partial pressure. No worries, no worries. If you don't count with the pressure data, just what you need to do is just relate that system with the system where you exactly know about the pressure data, right? About the pressure. It could be a partial pressure as well, no worries, right? Just relate these two systems, right? Okay. So I'm going to apply the visual control proportion is here now, right? So let's apply this stuff, right? So consider right? Consider what are the two systems? Total system, P total, total system at 327 Celsius, right? At 327 Celsius equilibrium, that system, and this system, that is what we know is for the component X, right? What we know the pressure is for the component X. So consider for the component X, right? X gas at 27 Celsius degree. These are the two systems we are considering. We considered only the X gas, right? On the total system here, we consider just the X gas here, as we know only the partial pressure of X. Now the total pressure we know only the partial pressure of X. That is why we consider only the X gas here, right? So when considering the P equals NRD for these two situations, right? V is a constant because it's a rigid vessel. V is a constant. R is always a constant. R is always a constant, right? So that, right, as V and R are constants, we can say P is proportional to NT. For these two equations, P is proportional to NT. So let's first apply the thing to the two constraint equations, right? So for 327T, let's apply. So P total, that is what we need. PT, that is what we need. It's proportional to NT, NT. If we are referring to total pressure, we have to consider total number of moles. So total number of moles is 0.7. 0.7 at the 327 equilibrium, at the 327 equilibrium is 0.7, and temperature is 327, that means 600, no? 601. Because in 27 Celsius situation, right? So pressure is 2 atm. 2 atm is 2 into 10 to the power 5 pascals, proportional to number of moles of X. Now we have considered is there. We are just considering X, right? If you are considering the PA, the NA should be applied, right? That is the point now. So if you are considering the partial pressure of X, only the number of moles of X should be applied, right? Okay, so that it is 0.2 moles. Because of the 0.2 moles only, this pressure applies, right? Only because of 0.2 moles of X, you get this pressure, right? That is why the equation is like that, right? And the temperature is actually 27 Celsius, that is 300 Kelvin. So if you are to divide these two, 1 over 2, will come up with PT into 2 into the power 5 pascals, that is equal to 0.7 into 600, right? The units to cancel, right? 0.2 into 300, right? So this will cancel off 2 here, and this thing will cancel off also 0.1 here with this one, and this will be cancelled off, right? As a 7 here, right? So 7 into 2 is 14 into the power 5, that is the P total. So this gives you for P total as 40 into 10 power 5 pascals. So P total is 40 into 10 power 5 pascals. Clear now? Right, that is the P total. So as you know the P total, this can be considered as calculation for someone too. As you know the P total, we can come up with the P set. We can come up with the P set. So P set, part of the P set is equal to mole fraction of P set into P total. So mole fraction of P set is actual number of moles of P set, 0.4 divided by total moles, that is 0.7 into P total. The P total is just found as 14 into 10 power 5 pascals. Right? So this will give you your P set as here, the P set as. So this is cancel of 4 to 7, no? 4 to 7, and this is cancel of that 7 as 2. So 8 into 10 power 5. This will be 8 into 10 power 5. So P set is going to be in 10 power 5 pascals. That is P set. Right? So this is how we are supposed to solve this kind of question. Right now? Okay, let's complete the stuff there. Let's do the question number 4. See what they are saying. 5 moles of NO gas and 2 moles of O2 gas was completely reacted in a rigid vessel at 27 Celsius to produce NO2. Total pressure of the vessel after the reaction is 180. This is a simple question number 9, right? Not hard one, right? So they have started with 5 moles of NO gas and some O2 gas, right, which was kept at 27 Celsius, right? So 5 moles of NO and 2 moles of O2 was there at the start, right? And complete reaction, right? Complete reactor. Produce some NO2 right? Produce some NO2, so NO2 is produced. Right, so the temperature is equal to 0, right? So in these questions, reaction happens without changing temperature, right? Okay. And after the reaction, the pressure is referred to as 180. Total pressure of system is referred to as 180. No? Total pressure of system after the reaction is 180 after the reaction. Right? So here the reaction occurs. Right? Reaction occurs. And after reaction, definitely NO2 will produce and 180. Right. So Lama, this is a complete reaction. This is a complete reaction. We are the 2 of NO gas reacting with O2 gas to produce the 2 of NO2 is referred to as a complete reaction. So if you are referring to complete reaction, one of these reactants should be a linked reagent, and that will totally consume at the reaction, right? If you are referring to a complete reaction, right, one of the reactants will be considered as a linked reagent, and that will end. That is why the reaction is referred to as a complete reaction. It's a complete reaction, right? It is denoted by straight arrows, not the double arrows like earlier situations, right? So let's find out the linked reagent as well here, right? So it's a complete reaction, right? So definitely one out of these two guys won't appear here, right? At the end of the reaction, definitely the products as well as the excess reagent will appear, right? So at the end of the reaction, the products as well as the excess reagent will appear, right? So this is the initial state. This is the end, right? It's a straight reaction. So at the end, surely the products and one of the excess reagent would appear. Excess reactant will appear. Right? Active reactants will appear, but linked reagent will end, right? See, let's say what will be the linked reagent here. So 5 moles of NO is added with 2 moles of O2. At the beginning, you don't have NO2, right? All the reaction tables are constructed for same temperature and volume situations, right? Right. So what would be the linked reagent here? So let's try. If you react 5 moles of this thing, you need half a number of moles of O2. That means for 5 moles, you need 2.5 moles of O2. But that is not there. 2.5 moles of O2 is not appearing. To react completely at the 5 moles, you need half amount of moles as O2. That means 2.5, but 2.5 is not appearing at the beginning, right? So 2.5 is not there. That means O2 is limiting. O2 is limiting. That is how you find the O2. That is how you find the linked reagent, right? Right? Okay. O2 is limited means at the end it will total consume. So at the end it won't appear. As it's a limiting reagent, right? Limiting reagent totally consumed. Totally consumed, right? Okay. Now come to the table here. So starting with 2 moles, ending with nothing. That means 2 moles have been reacted. So the change step order is equal to stoichiometry. 2 moles reacted means 2 times should react by this one. So that is 4 moles reacted number of moles, and this is going to be the same number, no? Plus 4, 1-to-1 ratio. So started with nothing, 4 moles produced. So ending with 4, starting with 5, and 4 moles reacted. So ending with 1. So your N total is going to be the summation of these three. That means N total is actually total number of moles at the end is going to be 5 moles. So now we can easily calculate that, right? partial pressures and the total pressure. So the partial pressures and volume. So partial pressures. Let's come to the partial pressures. So the partial pressure of NO is the mole fraction of NO into P total. The mole fraction of NO is number of moles of NO, that is 1. Total number of moles is 5. P total is referred to as 1 given as 180. So it is going to be 105, that is 0.280. So for the partial pressure of NO2, it is again P total. So NO2's number is 4, total number is 5, number of moles, P total is 180. So that is going to be 0.880. The final thing they are asking is the volume of the vessel. Volume of the vessel. So we can use the P plus N R to come up with the volume, because you know the T, you know the P, as well as you know the total number of moles as well. The NO is remaining, right? With 1 mole here, and with this one with 4 moles there, right? So NT is known, sorry, total number of moles is known, temperature is known, pressure is known. So for the total system, 3 variables are known. That means you can count with the missing variable there. So for total system, and you can apply the P equals in R. PTV is equal to NTRT, count with the V. Right? Total pressure is 1 million, so 1 into 5 pascals into V is equal to NT is actually 5 moles, R is 8.314, T is, which is 300 kV. So this is going to be 2 to 5 V is equal to 5 into 100 over 12, 300, no? So this cancels off. So 5 over 4. These things get cancelled off. So V is going to be 5 over 4 is 1.25 into 10 to the power minus 1. This is in meter cubes in SI units. That is the volume of the vessel. Right? Just complete the stuff. So when it comes to straight variations, what you should know is actually there will be limit gradient. First, just find the limit gradient, and then apply the end value of limit gradient as 0. That is the data here. This is a very important data here. Right? First find the limit gradient and apply the end value of the limit gradient as 0. Right? That the finding of the limit gradient is clear. So if you are with 5 moles of NO, to complete react that NO, you need half a moles of O2. That is 2.5 is needed. But you have only 2 there. Not enough O2 to complete react the NO. That means O2 is going to be limited. Right now? So there is limited. That means after that you can apply the end value of limited as 0. So that will help you to complete the table. That is 0, starting with 2, so 0.2 should consume. That means this state happens to is stoichiometric, so you can complete the stuff with the use of this knowledge. So that is info today's discussion. Right, that was all about the 3 questions appearing at the page number 12. Just complete these stuff and study well.